Hello, I'm Hugh Manfield and welcome back to the Fluid Space Theory Lectures. Today I'm talking about antimatter, and it's a fun favorite subject of mine. And once again, this is an alternative theory, but it's a theory that tells us more about antimatter than is currently known in mainstream physics. So you're going to see some new properties of antimatter that no one else in physics is ever going to be talking about, but they really need to know about it. So to help with that, you could pick up a copy of my book, Einstein and Aliens, and all the subject matter that I'm going to go through today is in the appendices of the book, and there's a science fiction story at the beginning that tells the same information, but in a storytelling format. So what is antimatter? Well, it's basically the opposite of matter. It's the mirror image, but the mirror image if you used a time mirror. And for every particle of matter, there ought to be an equal and opposite particle of antimatter. The problem is, when we look out into the cosmos, all we see is matter, and no one can figure out why. And there's a lot of different theories about where did the antimatter go, how maybe during annihilation between matter and antimatter there's a slight imbalance and a slight bit more of matter is created. Well, every experiment at the Large Hadron Collider shows that there's an exact parity in the creation of matter and antimatter. So why don't we see the antimatter? We don't see it forming galaxies and stars and colliding with matter galaxies and stars and creating a radiation pattern that we could detect, which is what people have been looking for. Well, maybe we're looking in the wrong place. An electron, antiparticle, positron, proton, antiproton, neutrino, antineutrino. Basically, if you flip the arrow of time, like run the clock backwards, an electron will behave as a positron. A proton will behave as an antiproton. So basically, when you reverse the arrow of time, matter takes on the role of antimatter, and antimatter takes on the role of matter. Now, we understand this through particle physics, but no one can really tell you why or how that happens, except fluid space theory can. If you think back to the inflow field of fluid space theory, the funneling of a sink flow creates a gravitational field. And that gravitational field includes length contraction, time dilation, everything you would find in the GR field of Einstein. But so far, we've only looked at inflow fields. And the math actually works exactly the same for an outflow field. So what if, instead of a sink flow with space-time flowing inward, we had a source flow with space-time rising outward? Would that kind of particle of matter be antimatter? Would it have anti-gravity? Well, let's take a look. In our flow field, for regular matter, velocity is inward, acceleration is inward. And we have a description of a particle of normal matter. Now, if we turn the outflow outward, we'll see that it's still fast, close to the event horizon, and it gets slower and slower and slower as it moves out the funnel. So the acceleration is still inward. I mean, it's decelerating outward, which is inward acceleration. So a particle of antimatter of fluid space theory would still have normal inward gravity. So if we look at that, here's an inflow particle moving forward in time. If we flip the arrow of time, it becomes an outflow particle. And if we have an outflow particle, outflow moving forward in time, which would be antimatter, if we flip the arrow of time, we get inflow moving backward in time, which would be normal matter. This is how, with fluid space theory, that antimatter and matter reverse roles with the reversal of time. It's because of the inflow and outflow direction changing. And this also makes it easy to see how a particle of matter and antimatter would annihilate when they came together. If an equal particle of inflow meets its equivalent particle of outflow, the two flow fields will cancel out and the energy will be released. So not only does fluid space tell us how antimatter and matter differ, it also tells us how they annihilate and why they annihilate, which is something you won't find in mainstream physics. So now if you think back to one of my earlier videos, I described how expanding space will slow an orbit and contracting space will speed up an orbit. So the difference that fluid space theory shows us between matter and antimatter is the matter will be an inflow and will be surrounded by a contraction field, while antimatter will be an outflow and will be surrounded by an expansion field. And this is a very important difference between the two types of matter, and it makes them behave in completely different ways. If we look at the contraction field scale factor plots, which reveal the dark matter signature around normal matter, we'll see that for different sized bodies, you'll reach a scale factor of 2. So what this means for normal matter is that the contraction field is contributing equally to gravity. But what this means for antimatter, the expansion field, is that if you get a factor of 2, now the expansion is nullifying gravity. It's contributing equally and opposite to gravity. And at a scale factor of 2, you will no longer be able to hold anything in orbit. Everything outside that radius will drift away into space. So when we look at the cosmic microwave background, we see places where it's a little bit warmer, shown in orange and yellow, and we see places where it's colder, shown in blue and light blue. And what this is interpreted as is that the warmer regions were areas where space was contracting and pulling in normal matter into stars and galaxies. And that the blue spaces, and we look out into the cosmos and we see that they represent voids where space-time is cooler and it is expanding. What fluid space theory tells us about the cosmic microwave background is that it may be a roadmap to where the antimatter lies. What you would see in the warmer areas is area where normal matter collected and began to contract together. And what you would see in the blue areas is where the antimatter tended to collect and began to expand, because antimatter is surrounded by an expansion field and matter is surrounded by a contraction field. So rather than a period of annihilation, what we probably had in the early cosmos was a period of segregation, where matter tended to clump together in a certain region and antimatter tended to clump together in other regions. So if we look at what happens to normal matter when it collapses into a black hole, we see that the scale factors go up to like 100,000 or more at different radiuses. So the contraction field becomes very, very strong and will help clump matter together. But what that means for antimatter is if you had a large clump of antimatter trying to pull together, the expansion field would quickly put a stop to that and disperse it back into space. And this is important to understand because in this case then, antimatter would never be able to form large stars. And large stars is where the nuclear furnaces create the higher elements. So if we look out into the cosmos, it's likely we will never see higher elements of antimatter other than antihydrogen and antihelium, which would be created at the beginning when the matter originally condensed out of the intense energy field. It's probably also impossible for antimatter to form a black hole. So there won't be black holes, there won't be supermassive black holes, and since these are what pull galaxies together, we'll never be able to see an antimatter galaxy. In fact, antimatter might not even be able to form even small stars. It may have just all dispersed out into the intergalactic voids. But this is where the science fiction author in me comes out, and I speculate, what if there was a period of time early in the universe where the conditions were right to form some antimatter stars? What would they look like, and where would we look for them? Well, first of all, it would have to be near the border between the antimatter region and the matter region, where maybe a matter supernova sets off a shockwave which creates a short burst of star formation in the antimatter hydrogen cloud, antihydrogen cloud, and then you'd have maybe a small star cluster of antimatter stars. This could have only happened very early, while the original clouds of hydrogen and antihydrogen were very dense, before they'd had a chance to expand and disperse. That would mean there was only a small window of opportunity to form antimatter stars, so if we found an antimatter star today, it would have to be very old, dating back to the origin of the universe. Antimatter stars would actually be very small. Anything above 1 solar mass, you would start to get an effective expansion field, which would prevent any further collapse. So it's very likely they would be small stars and very long-lived stars. They would be alone. Having no higher elements, the solar winds of these stars would probably blow all the hydrogen gas away, so you'd have a single isolated star. There would be no planets or small bodies around these stars because there's no higher elements to form that. And having an expansion field, they would not tend to collect any bodies out in the outer regions as our sun collects in the Kuiper Belt and Oort cloud. If you looked at the spectrum coming from these stars, they would be pure hydrogen and helium. They would only have higher elements that they would have created themselves over their own lifetime. If we found a small cluster of these antimatter stars, they would not show any dark matter signature or extra-gravity halo because they actually have an expansion field. There would be no dark matter signature or extra-gravity halo associated with a star cluster of antimatter stars. So what would happen if a cluster of these antimatter stars was caught up in the Milky Way's gravity and was absorbed into the Milky Way, as many small star clusters have been? Well, would they blow up? No, actually stars don't interact. So if there were these isolated antimatter stars, they could orbit happily within our galaxy. And what this means to me is that we should look for them, because our galaxy could be seeded with automatic fuel stops. Let's say we created an antimatter powered generation ship and we wanted to take it across the galaxy. Well, we'd only have to fill it up partially with antimatter, because if we knew where these antimatter stars were located, we could have fuel stops all along the way. You could fly your generation ship near the antimatter star, send out a collector probe, and scoop up a tank full of antimatter. So if this would be exciting to find, and something that no one else in physics is even talking about, whether there would be actual antimatter stars within our galaxy. So to sum it up, fluid space theory tells us several things about antimatter that we would never guess or never figure out through normal mainstream physics. First of all, antimatter has normal gravity. Antimatter is surrounded by an expansion field rather than a contraction field. Antimatter annihilates with matter because the flow fields are annihilating. So if you don't understand or know about the flow fields around matter in space-time, you would never understand this. Antimatter cannot form large stars, and therefore we will never find the higher elements that need to be forged in the cores of these large stars. No higher elements of antimatter will be found. And if antimatter did try to clump together, it would have a negative extra-gravity halo or negative dark matter, a repulsive dark matter cloud around it, which would tend to make it disperse. These are things that you would never know about antimatter unless you use fluid space theory. So until next time, I'm Hugh Manfield.